My name is Pawel Badenski, and today I wanted to chat about building high-performance web application, specifically financial web application with JavaScript, something that we've been doing for the past over 4 years in our startup. We started the journey actually more than 4 years ago, and yeah, I've been going since. I'm a CTO and Pricing Monkey. I'm one of the co-founders. I've been here since day zero. So this is going to be a journey of experience from that journey. You can see my Twitter, email. You can reach me out on those channels. I'm also a mentor at Meet a Mentor. If you haven't heard about it yet, do go ahead and check it out. It's a really cool and free community. I have nearly 15 years of experience in building software. I come from Java background, where I spent quite a bit of my past, and I became a JavaScript developer 5 years ago when we started the business. We're still going now. I do love design. I do love software philosophy, or all the different programming languages and all sort of problems. But I do love performance engineering. My love of performance engineering started relatively early in my career, and since it's really have been a thing I kept being drawn to. So yeah, so this presentation is our journey in 4 points. Something to say is my style of presentation is that I do tend to overwhelm people with information. So do take notes, things that you find interesting. So do take notes if you find something interesting. And feel free to reach out to me for more details, or if you want to hear more about any of what I'm going to talk about. It's going to be a bit of, like I said on the meetup page, there's going to be a bit of a buffet of information. I was trying to kind of cover for people who are just beginning their journey and people who are quite experienced. So yeah, get ready for a bit of a roller coaster. So first one, don't get distracted by other people's problems. This presentation included. I think it's quite relevant when you go to all sort of and I've certainly been a victim to all sort of conferences and presentations. You see, the new cool thing, the new technology, and immediately jump into it. And it's actually not necessarily the solving the problem your project might want to be solving. Everybody has their own problems and their own challenges, and the solution might not work across the different contexts. Now, we are a specialized software as a service platform for financial analytics. And what that means is our main JavaScript bundle is 6 megabytes, and that's 1.5 megs compressed. And everybody will probably run away screaming at this point. We're not bothered at all. We failed a Google Lighthouse test. This screenshot here is from Google Lighthouse, a tool that Google has in Chrome that can measure how well behaved your website is. We got 9 out of 100. First contentful paint, 5 seconds. For some of you, this might be absolutely horrific. Our customers go onto we have a small number of high-paying customers. They go on our platform and they open the page and they stay there for their day and maybe refreshing a few times in the day. It really doesn't matter that the page takes a little longer to load. So yeah, I know that 99% of the internet does care about that. We don't. So a lot of information that we find about performance, when I Google performance, website performance, or things like that in Chrome, I actually find things that are not necessarily as interesting to us. Yeah, majority of performance suggestions don't apply to our project. So the screenshot you see here is about Prometheus client. We do use Prometheus. Interestingly, actually, we do report metrics from Prometheus to metrics from each of our users. We report to Prometheus. I'll say a bit more about that a little later. So we basically track every single customer instance. We treat it as a separate node because we do some computation on the client's machines. We do also track need visibility in performance of how it behaves on each user's computer. So we push metrics from our users' browsers to Prometheus with a prom client library, which actually we forked in order to deploy it in the browser. Prometheus does not encourage, and they say it's an anti-pattern, but it has worked for us for 4 years. We have been recently looking at another technology that I do recommend you to check out. If you're using Prometheus and struggling, you might be interested in a tool called Victoria Metrics, which we've been recently looking to migrating to, and it looks very promising. And it, among other things, does support the push that we've been missing. So yeah, I mean, first thing that I would like to emphasize here is a lot of the time you might be using an anti-pattern and it actually works for a long time. So we've been doing this for almost 4 years, and only now with the scale are looking into a different solution. So context also have a longevity. I mean, Facebook has been using PHP and for a long time. So every performance suggestion will apply differently and might have a different context span as well. Our performance challenge, as I mentioned, is thousands of financial computations inside the browser. So here's a screenshot from Grafana. So these are the metrics we get from our users. And what you can see on this screenshot is that we calculate calculations on users in the users' browsers on their computers. There's around 200 calculations, each taking a few milliseconds, but 200 calculations every second. And that's something that we worry about. So we worry about what happens after user waited 10, 15 seconds for the websites to load. We worry about the next few hours, what's going to be happening as our financial data pulls a new live information, has to recalculate and recalculate. So what is our problem? Our problem is called, for us, it's optimization for a CPU-bounded situation with high event throughput. So what we deal with is 500 to 1,000 Redux actions per second. That's both system UI and non-UI. As you might guess, there's not going to be a lot of Redux. There's not going to be this many Redux actions coming from the user. A lot of it is actually being triggered by the system in order to manage incoming data and all sort of bookkeeping that is connected to handling live market exchange updates. Be talking a bit more about how Redux handles that later, but this is our reality. And another one is the 10 to 2 computations per second. So that's each other runs 10 to 50 milliseconds, which may take around 100 milliseconds to 5 seconds to perform a full sweep. So to recalculate 100 computations per second. With this throughput, to recalculate the whole user's context, the whole user's workbook, we might need up to 5 seconds. So of course, we offload it to a web worker. And that's something that's very specific to our use case as well, using web workers and offloading that CPU-bounded problem to a web worker. Otherwise, some of you node.js is single-threaded, so otherwise we would have absolutely no time for the user to be able to interact with the UI, with the user interface. So we need to move that to a separate thread, and that separate thread is in the web worker. So what's CPU bounded? CPU bounded is a fancy term, and when I've heard it a few years ago, I could never really get it. It sounded very exotic to me, but it's actually quite simple concept. It basically means that your program is mostly bounded by a CPU. So your program will go faster if you get more CPUs, or if you get your program run faster on the CPUs you have. It means that the emphasis in CPU bounded in comparison to any other resource in a computer like memory or drive or network, they don't matter. So you could have, if you have a CPU bounded problem, you could buy 100 terabytes extra RAM, but your program will actually still run the same speed, because the problem with this is with the CPU rather than with resources. To connect it back to the reality that many of us have every day, is most problems, the 99% problems that I mentioned earlier, a lot of those problems are actually part network bounded, part CPU bounded. So the faster your network is, the faster the website might render. Of course, the story is not as simple, because another thing with boundedness is that things kind of tend to, when you fix one problem, as in general in software development, when you fix one problem, another problem arises. So what happens is, when you fix a network boundedness, you often introduce another boundedness. So that happens with websites often, right? Like, so you make your JavaScript to be delivered to the customer really quickly, but once it's get delivered, they open it on its mobile, and then the mobile has a CPU that is too slow to load it quickly. So now you have a CPU bounded problem. So something to say here is, it's going to sound really obvious, but it's like 60% of success in performance optimization is to understand what's bounding your problem at every specific time. So you're actually spending your time smart solving a boundedness that's interesting. So there's no point optimizing how speed of your website if it actually takes long to load over the network. So that's something to remember. That's like essential thing in performance optimizations. Yeah, so a bit about JavaScript. JavaScript is faster than you thought, but slower than you wanted. And what I mean by that is, JavaScript actually, there's a lot of optimization that went into JavaScript, and it's actually a much different story when we started 4 years ago than it is now. It's faster than you thought because there's a lot of optimizations. So the JavaScript that you load actually gets optimized to a lot of the time to assembly code and to C. So things can run, especially when you run smaller bits of code, similarly to what you could achieve with C and languages like that. It's slower than you wanted is because as your code base grows and as the size of your project grows, it's much easier to break those optimizations or make those optimizations more difficult for the JavaScript engine. So yeah, so as you can see here, these days JavaScript is pretty fast. Unfortunately, JIT, which means just-in-time optimization, comes with caveats. Oh yeah, a bit about JIT. So the thing that I said, that JavaScript gets loaded as JavaScript and then gets compiled to assembly code and to bytecode and to C, that's called Java just-in-time optimization. And Java does the same thing. So actually behind the scenes, the code gets sped up, gets compiled into very fast machine code. And that's happening on the fly. That's why it's called just-in-time. In comparison, languages like Rust, Go, C, C++, they get compiled to to machine code, and that's it. They're super optimized at that point. So they don't go through this intermediary step. And the JIT, the just-in-time optimization, happens when you run the code. So that's important to remember. When you run your JavaScript, when the user loads it on their computer, that's when the optimization happens. So something that you see on the screen is just merely assigning a function, math power function, to a variable and then calling it will slow it down. And that's called to some, I dug it up from a blog from 2013, so this might not longer be a case, but that was a case, and there's a lot of things like that still in V8. A lot of these things get fixed, but those are the type of challenges that you get, that some things just are totally unintuitive. But unfortunately, the byte, when JavaScript is compiled, the bytecode changes, and the engine is not able to optimize it out anymore. And in this example, you can see that the slowdown is 1 order of magnitude, so it's 10 times slower. There's some more practical caveats. It was pretty big a few years ago when the V8 update accidentally broke React. There was some interaction between different functionalities, between different features, prevent extension back in V8, and suddenly React, when executed on a complex use case, would run slower. You can read more about this. It's a pretty in-depth problem. But also what's important to kind of mention here is that you might not have to deal with this sort of problems day to day, but they do matter in case of frameworks or libraries. So things that get called a lot under the hood. So where your business code, in your domain code, in your high-level code is not going to be that's super important. The lower you go in terms of your architecture, the more relevant that might be. Of course, as usual, it will depend on your project. Other challenges. So here's going to be a big mishmash, a big all-you-can-eat buffet of examples. So there's a lot of string representations in JavaScript. I mean, I found this on Stack Overflow. I'm not sure if I haven't been aware before that, but actually you have one string in JavaScript, but this can, depending on the context, be represented in actual V8 engine in 10 or 15 different ways. And it's very difficult to know which way it is. And all those representations have different performance characteristics. So something that I wanted to really put a warning here is be careful. That's another point, to be careful with your micro benchmarks. Because what we noticed a lot is we run our micro benchmark and it has totally different performance characteristics than production code. Because production code might run on a different string and you don't even know that it's running on a different string because it's very difficult to inspect. So you have to be very careful when you try to optimize production code and you try to create your micro benchmark and you're like, oh, I optimized the hell out of it 10 times faster. And then you deploy it and actually it didn't change because it used a different representation and there was different behavior in a GIT optimization. So be very careful with micro benchmark. I can't emphasize it bad enough. Like 95% of the time, I see a micro benchmark, I'm like, no, it's wrong. And it might sound a bit arrogant, but unfortunately, that's the reality. It's very difficult to do these things. There's other things that hurt us a lot is there's no hash code in string and there's no interning. Interning is a process when you can flatten a representation into faster representation, something that Java has. And a hash code is a very important feature when you use data structures like maps and sets. For us, it hurts us a lot. A lot of array representations. Again, this comes with the same caveat. Be careful. You think you have one array, you think you did your micro benchmark, but actually you have all these representations, and actually they will run with different performance characteristics. They can be up to 5 times performance difference between them. Something that many people are not quite aware about: object polymorphism, megamorphism. So this is that Java doesn't have, and this is one of the. If there's one thing to remember from this presentation, it might be this. So because JavaScript is dynamic, it optimizes based on execution. So JavaScript will optimize your code based on the shape of the data that comes into the function. So if you call your function with just numbers, JavaScript will notice it over time and it will say, oh, amazing, you're just giving me numbers to this function add. That I'm going to optimize it into very efficient machine code because you're just giving me numbers. But if you have these multifunction methods, or you actually using your methods a bit haphazardly, and you give a string, you give a number, you give a boolean, you give an object, JavaScript will be like, okay, dude, I don't know what you're giving me. You're giving me different objects. I'm just going to use the least efficient code so I can handle all these different cases. So that's something to remember. Things are optimized based on usage. So making it obvious how you're using it will make it faster. Will make it faster for another programmer as well, because having things that are like a Swiss knife are actually difficult to understand by other developers on the team as well. And a tool that's really cool to check out for this if you're interested, but be careful because you can get stuck for days and days with this and it might not be relevant for your project. It's called deoptigate. It's a really cool tool to see how your objects, how your code gets optimized or de-optimized. Oh yeah, something that I wanted to add here very quickly is the megamorphism also applies to dictionaries and objects. So a bit of trivia, I don't know a bit of trivia is like, if you line your keys in an object different way, this will be actually considered a different object in JavaScript. So if you say first name and last name in your object, and then you spread it, and then you add first name second, this will actually be different representation. So if you're using spreading a lot in your, and you have large objects and you're spreading a lot in your project, this will have impact on performance. Something more relevant to us, again, slow data implementation, something that is kind of interesting because there's a bit of a tension between us and the rest of the world. Like I mentioned earlier, we want JavaScript to run really fast on those CPUs. The rest of the world is kind of like happy with, and rightly so, Is WebAssembly an alternative? Everybody keeps asking me that. Maybe. I'm very skeptical about it. Something to really emphasize here is WebAssembly is still JavaScript. Is still the same engine. So WebAssembly still runs in a V8 engine. There is some opportunities for writing more optimized code in WebAssembly. You can maybe scale your code base better to be able to leverage the just-in-time compiler and optimizations, but it's not a silver bullet that everybody says it is. And also, there's still a lot of things in WebAssembly that aren't quite there. For more details, there's a presentation that explains it in depth. It's a half-an-hour presentation just focused on this topic. That was JavaScript being fast. Now pick your battles. We chose React and Redux. Maybe you could have chosen something more lightweight. We're quite happy. Something to kind of was a takeaway for me. It's okay to choose a popular solution. We have evolved some of the popular libraries we use. We have evolved our asynchronous management, for example, a lot. We used Redux Saga for a while. We used Thanks. Now we use some half homegrown solution based on RxJS. But React and Redux stayed with us for a long time, and it kind of is just enough. You can get used to living with it. We use, on top of Redux, we optimize for performance, of course. So we use immutable JS, which we still use it, even though I know the rest of the world is kind of walking away from it, but we do really need it for performance. I mean, we're quite sad that it's half abandoned. Reselect quite extensively for creating our transformers and a few other tools. Something we learned about React is not necessarily very reactive. I'm very sad about this. No, it's no built-in debouncing of rendering. So you basically can't say, okay, if this component gets called a lot, just ignore 90% of the renders and just render every 200 milliseconds. Worse even, there's no debouncing of prop updates. Many of you may have not even come across it. It's very specific to us. If you're calculating props is very expensive, you actually do want to calculate your, for example, every half a second or every 1 second. We use lazy data structures to facilitate that, so it's a bit of a hack. I've read recently that apparently somebody come up with a solution with React hooks, so maybe we're getting there. But this one was very frustrating to us for a long time, because there's a way to debounce, and a lot of people do this debounce of rendering, but many don't get this problem of like, okay, but what if I need to debounce my prop updates as well? Overall, we're quite happy with React, and it's with the few workarounds that we have, it's working out very well for our use case. Okay, so interestingly, last but not least, great performance will always start with great design. This is a massive topic, so I'm only going to mention a few things here. But first of all, focus on good architecture, good design first. I see some people optimizing their algorithms and making like really efficient solution and saying, hey, look, it's really fast. And you can't really then maintain it or read it. And there's a lot of like hacks and tweaks. And really what's important, if you want a long-lived solution, you want to optimize for fast feature delivery, right? So performance is just one of the requirements. So you want to write a performance application so as performance as possible, but not more. So you kind of want to make sure that you can write your features as fast as possible, and at the same time optimize where it's necessary, and not even 1 inch more. So yeah, can't back, make it work first, refactor, and only after you measure, make it fast. And when we optimize, we always optimize systemically first and tactically second. So what I mean by that is you want to do optimizations that redesign, change your design in a way that's still very readable, but faster, rather than doing one of these, okay, let me use these tricks to make my algorithm go really fast. Those, you should always be very careful and do as few, those tactical, local optimizations that make your code look worse. You should be very careful with those, because they will hurt you. This is a screenshot from the OptiGate. This is what it looks like. Try it out. It looks a bit cryptic, but it's a very useful tool to understand how your code gets optimized. And you can see there's a very complicated code from some parser, Babel or something like that. And you can see the code that's complex to read by your fellow developer actually will be difficult for the machine to execute. A lot of people don't, or even you don't even think about that a lot every day. The simplicity of the code translates to simplicity to read, but also translates to simplicity to optimize. So if you keep your methods relatively short, if you keep your objects simple, if you keep your design well factored, you're probably potentially just getting a faster application. Evolving great design, topic of 1,000 presentations. So we use TypeScript. Perfect, best tool for fast code because it deals with megamorphism that I mentioned earlier. It helps you create predictable design. It helps you manage a complex code base. So if you follow the patterns that TypeScript advises, actually, you're much more likely to get a nice well-performing application. Something that we took a lot to learn, and I would definitely recommend you don't make the same mistakes as us. That the book Effective TypeScript wasn't there when we started. It's there now. If you're using TypeScript, it's an amazing source of knowledge. We had to learn a lot of it through our mistakes. Monad, really useful for managing complexity. Something that we use to handle a lot of the time to represent exceptions. So we use either monad rather than exceptions. We use option type to deal with nullability and other monads to basically encapsulate the complexity. Something that's I've not seen as popular in JavaScript community, but is being quite popular in Java, is especially for us, we have a monolith because most of our application is a tick client that gets deployed on user browsers. So it's very important for us to manage dependencies in this monolith very carefully. So we use Dependency Cruiser, which basically allows you to manage dependencies between different modules and not for it not to get out of hand and become the spaghetti code of everything talking to everything. We built a thin layer on top of it, which we got inspired by ArcUnit. ArcUnit is a solution in Java, which is much more extensive, but you can borrow from that tool in order to build your simple domain-specific language for dependencies. Yeah, and we do leverage domain-driven design, for a way to making sure that our code base is close to the actual problem, domain problem, and to manage architecture at scale. So in order to factor our modules, to manage dependency between them in a sane way. I mean, something that's really useful with domain-driven design is if you have your modules structured around domain concepts, you know that if there is a dependency between modules in the code, there should be a dependency between modules in the real life. So when you see there's dependency in the code, but when you look at the real life, there doesn't seem to be a relationship, you should say, okay, something is wrong with our code. So it's really useful in that. That's one way how domain-driven design is useful. There's many other ways. If you want to start simple, the best way to start, I think personally, is to check out Redux, which is a library helps you start this journey in Redux. So yeah, in summary, don't get distracted by other people's problems, including this presentation. You might have a different problem than other people, and that's okay. JavaScript, faster than you thought, because a lot of things gets optimized for you, but slower than you wanted. Because if you're not careful, a lot of things will not get optimized and will remain slow. Pick your battles. You don't always have to have a new shiny technology. You don't always build something yourself. You can just pick the most popular thing first and then iterate. And last but not least, remember that great performance, there's a lot of tricks to great performance. There's a lot of knowledge how to optimize things, but you start with great design. Actually, things might just get optimized for you most of the time. And even as you go, optimizing things is gonna be much easier. Thank you. That's it really for the all you can eat buffet of tips and tricks from Performance World.